Now, the first thing we need to do before we design anything is to get a very clear definition of what it is that the circuit is supposed to do. You might take this for granted, but actually you'll find that many times either yourself or someone who wants you to build something for them really can't explain in detail what it is they want you to build. So the best way to do it is get a very, very clear description in writing and try to make it as short as possible. Don't have any extra baggage in there, but also have it so that if you take any one element out of the description, that it won't be adequate. So here we have a description of the circuit we want to build. Basically its behavior is going to be pressing a button should toggle the state of the LED. If it's off, it should turn on. If it's on, it should turn off. But another very important criteria is that the LED should not change state until the button has been fully released and then pressed again. You will find if you design a circuit like this that you'll get all kinds of odd behaviors if you don't describe it very, very carefully like this. Well, now that we have a good verbal description of what it is we're trying to accomplish, we want to create a drawing. Remember, a picture's worth 1,000 words. And what we want to do here is we want to create a state diagram that describes the behavior of the system in more detail, but follows the word example that we already have. So what we do is we have a state diagram here that shows 4 states. You may wonder, well, why do we need 4 states to turn something off and then on? Well, remember, if you have a light switch and you flip it on, it's on. When you flip it off, it's off. And here we're asking the system to be able to accept a switch closure and change states, and then release the switch closure and then go to another switch closure and change states again. So if you really think about it, you have 4 states there. You have up, down on the switch. So, or open, close, open, close. So here we have, we come into our 0, 0 states. We have 4 states, 0, 1, 2, and 3 in binary. And what we do is we enter here and we say, do we have a switch closure? If we do not have a switch closure, the button is not pressed, we just spin in this loop. We just stay right here and spin. As soon as there's a switch closure, we can change states now, and we also, because this is a melee machine, we indicate our output here. So this is basically saying, 1, turn the LED on. So this is our input and this is our output. So we've got a switch closure, we come down here to this state, but now here's the tricky part about this where a lot of people make a mistake. If you had the system set up the way most people would, because your button was still pressed or your switch was still closed, you'd go tearing right through this state and you would basically be turning the light off and on as fast as the clock cycle was cycling the state machine. So what we do here is we're a little smarter. We come down here and we say, hey, wait a minute now. Is the switch still down? Is the button still down? Is the switch still closed? If it is, let's just wait here. Okay, let's wait here until they release the switch, which switch not, but we still have the LED on. And when we come down here, now we're going to spin here with the switch release, the button up. We're spinning here with the button up, and we're waiting for the button to go down and for the switch to be closed. When the switch is closed, we can go on to the next step, which is step number, this 4th state, or state number 3, and that means that the switch has been pressed, the switch is on here, but now we turn the LED off. So all the way through this side over here, the LED was on, and we're waiting here for the button to be pressed again. Now all the way through this side, the LED's off. So here we do the same thing, and we're waiting for the switch to be released. So as it says, is the switch on? Is the button down? Yes. Is the button down? Yes. Yes, yes. And then when they release the button, zoom up here to the 0, 0 state again, and start the whole process over again, waiting for a button closure. So that's why you need 4 states instead of 2, is because otherwise when you press the button down, you would just spin around and around and around. You have to wait until that button is released. We've developed a clear verbal description of what it is that we want to design, and from that we were able to generate this state diagram that shows in graphical form what the verbal description described, and that is how the system behaves from one state to the next. From that, what we're going to do now is to generate something called a next state table, which puts that information into tabular format, and we can start our design process from there. So what we have here, the yellow column here is the current state, the blue column is the next state. And we have 4 states, 1, 2, 3, 4. But in each state row, we have listed 2 rows of that state because we have that state with the switch off and that state with the switch on. So here we have state 0, 0 with the switch off. What next state do we go to? Well, we stay in the same state. We go to 0, 0 again. But here we have state 0, 0 with the switch on. And then we go to state 1. And this is basically just putting in tabular form exactly the same information that's on this diagram, the state diagram. So we go down through all of the states. In this case, we have 4 states and we only have 1 input variable, which makes it easy. So since we have 1 input variable, we have 2 conditions for the input variable. So for each state, we're going to have 2 rows. If we had 2 inputs, we would need to have 4 rows for each one. But here we only have 1 input, so we have 2 rows. So switch off, switch on, switch off, on for each one of the rows. And then over here we have where we're supposed to go to based on whatever state we're in and whatever condition that switch is in. Now, once we have figured out what the next state is going to be based on the input position, now what we have to do is figure out how do we get the flip-flops to behave the way we want them to. Here we're going to use the JK flip-flop. And the reason we use the JK is it has a tremendous advantage over all the other kinds of flip-flops there are out there. And the reason is because if you hit the J and the K simultaneously, it toggles the output bit. So essentially what the JK flip-flop is an SR, or a set-reset flip-flop with an additional capability of being able to toggle. This gives you more flexibility in your design, and it also simplifies the logic that drives the JK flip-flop, because what you get is a lot of don't care conditions. It doesn't matter whether a bit is set or not because the results will be the same. So that gives you a tremendous advantage. So what we want to do here is we want to take all these conditions where we've defined our current states, the state bits, Q and Q0 and Q1, those are the state bits, and we want to figure out, based on the present state, how we need to manipulate the flip-flops in order to generate the next state. So the way we do that is for every condition that we have defined here, for the switch being off and on and being in the various states, we look at the Q1 and the Q0, and we say that the Q1 is going to be managed by this JK flip-flop here, JK1, and the state bit Q0 is going to be managed by this flip-flop here, which is JK0. So what we do here is, understanding the way that the JK flip-flop works, we have to define whether the K, the J, and the K input should be addressed with a 1, a 0, or whether we don't care. So the way we do that is, just as some examples here, let's say we go from here, we go from a 0 on Q1 to 0 on Q1 next, and for a JK flip-flop, it basically says, I don't care what you do with the K, the reset. I don't care what you do with that. If you hit it with a 1, it'll work. If you hit it with a 0, it'll work. But whatever you do, don't hit the set, because we want to keep it at a 0. We don't want to set it to a 1. So you'll find that for each one of these conditions, from a 0 to a 0, from a 0 to a 1, from a 1 to a 1, and from a 1 to a 0, you will have the conditions of the JK flip-flops that can be set up to meet those conditions. So let's use another example here. Here we have, we're going from state 0 to state 1, so the lower bit, the Q0 bit, is going to go from 0 to 1. So this JK flip-flop here handles that bit. How are we going to set that bit? And it says, I don't care what you do with the reset bit, just hit the set bit, hit the J bit. The reason is because If this was 0 and you hit the set bit, the J bit, it's going to set it. If it is a 1 and you hit the set bit, and you have a 1 in a 1 condition, you're going to toggle. So here it doesn't matter. You can either set it or you can toggle it. You're going to come up with the same advantage. So what this does is it gives you a lot of flexibility in your design with the JK flip-flops that allow you to use a lot less logic in order to build your systems. And that's really a big help. So now we've finished with our next state table, which is simply just tabularizing the state diagram that we have in graphical form. It's just basically a tabular form of the state diagram. But one additional thing that we did after we just transferred the information from the state diagram into a table, we came up with the JK flip-flop excitation table. In other words, we had to figure out how do we get the JK flip-flops to generate our state information correctly. Also over here we have our LED information on this next state table. It says based on if we're in state 0 with the switch is on and we go to state 1, then we turn the LED on. Now that information is also on this state diagram. That's the information that you see here after the slash, which is our output. So I haven't bothered, just so it doesn't clutter up the table, to put in the zeros. I've only put in the ones. Everything that's left empty here basically would be a 0 on that state table. So once we have that, what we want to do is we want to create another diagram, which is the Karnaugh map, or Karnaugh map, however you like to pronounce it. And what this is an amazing tool that allows you to reduce all of the Boolean equations to a graphical format. And the first thing we need to do is we need to transfer the information out of the next state table that we had into this map. And the way that we do that is we take this information right here, the ones and zeros and don't cares for the J and K flip-flops, and we put them into this table. All of this information is available if you just request it. It will be a lot easier if you actually are holding it in your hands and looking at it. The only trick here is that we need to switch the states of 0, 1, 2, and 3. We list them out this way in this table, but we want to rotate. We only want to have one bit changing at a time, so we go to a gray code. It's 0, 0, 0, 1, 1, 1, 1, 0, instead of having these two reversed. What this does is it greatly simplifies our logic, and it makes life a lot easier for us. But you have to remember to arrange your states in a gray code so that there's only one bit changing between these columns. So here we have state 0, 1, 2, and 3. Excuse me, 0, 1, 3, and 2. And the same here, 0, 1, 3, 2. And this is for the J flip-flop. So this is J1, this is K1, this is J0, and this is K0. And you might want to sort of stop the video and take a close look at this table. Maybe I'll zoom in on it a little bit more here so that you can see it better. But what this does is it transfers the information out of this table into this type of format. So you say for the J1, if the switch is 0 or 1, in state 0 we do this, in state 1 we do this, in state 1, 1 we do this, in state 1, 0 we do this. And it's if you look at these two, you will see that the information is transferred straight out of one into the next. So what I'm going to do now is I'm going to zoom in on both of these, and so that you can stop the video and take a closer look at each of them. Alright, here is your next state table. Here are your Karnaugh maps. Now you will notice that when this is done, you can actually write out the equations for your J1, K1, J0, K0, and your LED. And after we're finished with the Karnaugh maps, we have all the information that we need to draw our circuit. All we have to do is to connect the logic in such a way as it describes the equations in the Karnaugh map. So on this schematic, which again all this material is available if you just request it for free, these equations represent exactly the same information that came out of that Karnaugh map. So we design the circuit, we draw it up, and we build a prototype. Here's the breadboard for the one switch off on Finite State Machine. It uses 5 chips. This first chip over here, U1, is a 556 timer which incorporates 2 555 timers. These LEDs that are flashing right here are the T1 and T2 period off on of the left side of the chip, the first timer. Now they might look like they're oscillating in and out, but actually they're steady. That's just the interplay between their flash rate and the scan rate of the camera. So I have set up a cycle rate, a frequency of about 28 Hertz, which is fast enough to where it's faster than you can get your finger off and on the button, but it's also slow enough to where you can see it flashing and it's not just looks like they're both on. It's about 28 Hertz controlled by this capacitor right here and a couple of resistors. So the second chip here is the 107, which is the dual JK flip-flop. Then we have 4 AND gates, 2 input AND gates here. That's a 7408. This chip right here is a triple 3 input NAND gate, a LS or HC, whatever you're using, 10. And this last chip right here is a hex inverter, 74 HC04. This is the LED over here that we're controlling. It's off right now, and here's the button. So according to our state diagram, and what we're trying to accomplish here is that we want to be able to turn the LED on when we press this button. I'm going to press it, it turns on, and I've released the button. And when I press it again, I want it to go off. So the functionality of this circuit is when you press, it goes on. When you press again, it goes off. And of course, this is actually 4 states. You've unpressed is one state. When I press it down and hold it, that's another state. When I release it, that's a 3rd state. And when I press it down again, that's a 4th state. So there's actually 4 states in here. 1, 2, 3, 4. Let's just sum up by going over the steps of this design methodology. First thing you want to do is you want to come up with an accurate verbal description of the problem. Then you generate a state diagram from the verbal description. Next thing you do is you take your state diagram and you convert it into a next state table, adding additional information about how to excite the flip-flops that you're using in the system. In this case, we're using JK flip-flops, so we have a J and a K input for each of the flip-flops. How do you generate the inputs to the flip-flops that will give you the proper next state output bits? Then you want to take that information and you want to generate your Karnaugh maps from it. And this is a process that you just have to look at some examples to see how it's done. But the main thing is to make sure that you transfer your states into a gray code so that you only have 1 bit changing at a time. This will simplify your logic quite a bit. So when you go to design your circuit, you'll need a lot less gates. Then once you've come up with your Karnaugh maps, you generate the Boolean equations directly from your Karnaugh maps, not only for the next state Q bits, but also for your output that you want from the system. And once you have that, you're ready to build your circuit. You just need to define what chips you need to do it, sketch it out, and figure out generally what kind of chips you have and how you want to switch from positive to negative logic, whatever you want to do to get it done. But basically, you're just implementing the Boolean equations that you got from your Karnaugh maps. And then once you have gone through the system several times to make sure you haven't made any mistakes, then you just go ahead and prototype the system and test it. So if you need any of this information, just email me and I will send it to you for yourself or for your class or whatever you want to do. So good luck, and we'll see you next time. Take care.